In this example, we're going to learn to find the prime factorization of a number. So thus far, we've decomposed numbers multiplicatively by finding all of its factor pairs, and we've also learned to determine whether a number is prime or composite. Now our goal here is to keep factoring a number until all the resulting factors are prime numbers, and then write the number as a product of those primes. So we're going to use a method called factor trees. And basically what you need to do is you look at the number and think of any factor of the number. If you can't think of a factor, you can try the process we already learned. Try dividing by 2, 3, 4, 5, 7. Okay? But if you can think of a factor, it doesn't matter which one you start with. No matter what, you'll get the same factors in the end. So the first one I think of when I see 12 is 3 and 4. So 12 is 3 times 4. So I'm going to keep a little chart here just to keep track of the factorization. So this is a factorization of 12, writing 12 as a product of two or more numbers, but it's not a prime factorization because 3 is prime but 4 isn't. So once I see a prime number, I'm going to circle it. And if a number is not prime, I'm going to keep factoring. So 4 is 2 times 2. So now I have 3 times, and instead of 4, we wrote 2 times 2. And 2 is prime. So I'm going to circle those 2's. And this is my prime factorization in factored form. So typically, we write the factors in increasing order, so I'm going to write the 2's first, so they're equivalent, remember, because of the commutative property. I'm going to write 2 times 2 times 3. And remember our exponential form, well, this is 2 factors of 2, so we'd write that as 2 factors of 2, or this would be the 2 factors of 2 times 3. So there are our two forms. Let's look at the next one. So the first factor I think of when I see 75 is 25 times 3. So there's 3/4 and 75 cents. But again, you could use 5, it's divisible by 5, and find the other factor pair as you go. So I'm going to do 25 times 3. And I'm going to write my results here. And this isn't necessary, but I think this shows you how we're keeping an equivalent number as we continue along. Notice 3 is prime, so I'm going to circle it. 25 is not prime because it's divisible by 5, and it equals 5 times 5. So if we went down another step, we change the 25 into 5 times 5, and then bring down the factor of 3 also. 5 is prime, so I'm going to circle them. And then these are our 3 factors. And again, I'm going to write them in increasing order, so I'm going to write the 3 first. 3 times 5 times 5. In exponential form, we have 1 factor of 3. We don't write the exponent of 1 when we have that. And then we have 2 factors of 5, so 2 factors of 5. So that's our exponential form. Now let's look at one more. So 155, well, I see it ends in a 5, so the first thing I want to do is divide it by 5. Just going to go to the calculator and divide 155 by 5, and we get 31. So I know that 5 is prime. Now is 31 prime? Well, that wasn't in our list of the first few primes. Our list went up to 19. We had 2, 3, 5, 7, 11, 13, 17, and 19. And we didn't go up far enough to see if 31 was on our list. And I think it's prime, but we should really check this. So notice, since 31 is between 5 squared, which is 25, and 7 squared, which is 49, to just double check to make sure it's prime, we're going to check 2, 3, and 5. Okay. Well, 31 is not even, so it's not divisible by 2. It doesn't end in 0 or 5, so it's not divisible by 5. And 31, you can think if you divided 31 by 3, well, 3 times 10 is 30, so there's going to be a remainder of 1. But if you need to double check, you can just always do that on the calculator to make sure. And notice we have a remainder. So it's not divisible by 3. So that means 31 is prime. And that's our prime factorization, 5 times 31. The exponential form in this case is actually going to be equivalent because since we didn't have a repeated factor, we would just repeat writing the 5 times 31.